One, find the potential inside and outside uniformly charged solid sphere. Uniformly charged, okay, not shell. Is that okay? Uniformly charged solid sphere of total charge q, radius r. Uniformly charged solid sphere of total charge q and radius r. Is that okay? Now I told, whenever Gauss law allows us to find electric field, find the electric field, then go for I think we better to do in both way. We better do in both way. I mean, one is Gauss law route, other one is integral. This is a finite charge distribution. Am I right? Now we got two different way. One is, this is finite charge distribution. Potential at any point is infinity to r E bar dot dl bar. For that, you should first find electric field. Gauss law will help us to find electric field. Spherical symmetry. Okay. Another one is V of r. I don't know whether this is simple or not. This may be difficult. Am I right? You need substitution. You need integration by substitution. Better to avoid this one. Okay. Anyway, initially you are preparing for what you call multiple choice question. dq by r. Let me write again, rho d2 divided by r. dq is equal to rho d2 if you go for specific one. Okay. So now again, these two can be applied. Infinity as a reference point because finite charge distribution, or this is also, I mean, derived out of this one only, am I right? By solving this one for one charge and generalizing it, isn't it? This for finite charge distribution, obviously. Is that okay? That's why, again, which one you choose? You have to choose this one because that integral would be lengthy. Or you can check it out in the solution manual. Now, so I have to find electric field, okay, in two different regions. So this is uniformly charged solid sphere. What is rho? Q by 4 by 3 pi r cube. This Q is uniformly distributed. That's why charge density is total charge by total volume, isn't it? So now, outside there is no charge. If I want to find electric field outside, what should I do? I have to take one Gaussian surface which is passing through that point, centered at the same point. Is that okay? Or concentric with the sphere. And then I have to take Gaussians, I have to apply my Gauss law, am I right? E bar dot dA bar is equal to, so close the surface. This is the surface. Can I take S1? Surface S1. So that's equal to Q enclosed by epsilon naught, isn't it? Q enclosed by epsilon naught. I told for a spherical symmetry problem, this part would be same, am I right? Or let me do it in this way. So throughout the surface, electric field is constant. Modulus of electric field is constant. Throughout the surface, electric field and dA vectors are in the same direction. That's why I can write it as electric field will come out of the integral, closed integral of dA. Cos 0 will be there. Can I write like this? That's the easiest way, without getting into coordinate geometry, am I right? Earlier I have done coordinate geometry. I have written dA, r, and I expanded that one, and then I substituted the theta, phi values. So I mean theta, phi integral, am I right? You can do like this also. Because what is this one now? This is the surface area of the Gaussian surface. You know that one. If this is of radius r, what is the surface of this spherical Gaussian surface? 4 pi r. So you can directly substitute. Okay. So and Q enclosed this Q. Net charge enclosed by this one. He said total charge Q is distributed. He already said. Okay. Total charge Q is distributed throughout this one. Total charge is Q by epsilon naught. Okay. And what I am saying is this part will be same for spherical symmetry problem. And these parts will be same for all respective symmetry problem. You can just check it out. Okay. So now mod E into 4 phi r square is equal to Q by epsilon naught. So electric field 1 by 4 phi epsilon naught Q by r square r cap. So why it is along r cap? That's what we first inspect. Am I right? I mean, so by inspection, you have to first find the direction, then you have to find the dependency like that, isn't it? Now look at here. Now you don't have to again think of all of those earlier arguments. Electric field should be along r cap. Now by practice, you have to write it quickly. Is that okay? So to convince that one, I have done those arguments. What is that? How I can take this electric field outside the integral. Electric field depends only on r. Over that surface of radius small r, electric field is constant. Modulus of electric field is constant. That's why we can take out. And electric field and area vector are along the same direction. Now I argued like that, but in any spherical symmetry problem, you have to quickly write this step directly. You should not waste time. Now onwards. So now onwards. Initially, you have to argue, you have to understand that one, what is happening over there. Is that okay? So next one. This is E out. Can I write E out? That's better. Because for the point outside. For the point outside. Now, so for the point inside, again I have to take Gaussian surface. Spherical symmetry, okay? Again, all arguments will be same. Electric field will be along r cap and electric field depends only on radial distance. All arguments remain same. So that's why I have to take Gaussian surface, spherical shape of radius small r. Now this r is less than capital R. Okay? For r greater than capital R. Okay? Or shall I take it here? R greater than capital R. Case 1. Case 2. Case 2. R less than capital R. I mean inside. So now again, this part is same. Can I write directly? This part is same. Isn't it? So that's why I can write it as modulus of E into 4 phi R square. Now R is less than R. But whatever, that arguments are same, right? Again, you have to write this step, or you can write it as S2, surface S2, which is within the sphere, okay? Now, 1 by epsilon naught Q enclosed. What is the enclosed charge? Now, enclosed charge is charge within this region, am I right? Again, I am doing that Gauss law problem again. But you have to do it in very less step. Is that okay? Because your ultimate aim is to find potential. Is that okay? Yeah, now look at here. 1 by epsilon naught into, can I write it as rho d2? Why? I need charge only within this this surface S2. Can I call this one as V2? V2 is the volume enclosed by S2, surface S2. Is that okay? So now, how do you write that one? Q enclosed, V2, rho d2. Rho is constant. What is that rho? Q by 4 by 3 pi r cube. What is this one? V2 d2. What is this one? Integral of d2 V2 throughout that volume. That is volume of V2, isn't it? Now again, you don't have to go for coordinate geometry. You can write that one r square dr sin theta d theta d phi. You can run those integrals, but it's not needed. Look at here. Once that rho comes out, isn't it? So what is this one? This is the volume, isn't it? Volume integral of volume element. This is the complete volume. Complete volume of this one. What is the radius? Small r. Isn't it? Q by 4 by 3 pi r cube. 4 by 3 pi r cube. Okay, but I suggest you to write this integral, because if rho is a function of r or something, then you have to do that integral, isn't it? So that's why you have to take care. Again, rho will be function of r only, okay? Otherwise, we can't use Gauss law. Otherwise, it will not be a spherical symmetry problem. Is that okay? If rho depends on theta, I mean, if charge density is higher in one side, lower in other side like that, then that's not spherical symmetry problem. We can't apply Gauss law. Okay, rho, it will be function of r. If they give any functionality, it will be function of r only, radial distance. Okay. Now again, Q, r cube by r cube, am I right? So now if I substitute here, what would happen? E into 4 phi r square into 1 by epsilon naught Q r cube by r cube. I think I can, yeah, how do you write? E outside was 1 by 4 phi epsilon naught Q by r square r cap. E inside, where r is greater than r, so E inside. Somebody should have asked one question, what is on the surface, isn't it? Yeah, wait a second, we shall think over it. One of the r remained in the numerator, remember. One of the r remained in the numerator, 1 by 4 phi epsilon naught Q r by r cube. Obviously, it is along r cap. That was the argument. That argument should be there in the beginning. Okay, for r is less than r. What is on the surface? Is that continuous? continuous. You get that? So put R equal to capital R, you will get these two matched. Okay, it is continuous. You can put less than or equal to. Is that okay? Again, when it will be discontinuous, let me discuss. Next one is boundary conditions. Whenever there is a surface charge, it will be discontinuous. Let me discuss that one. Now we don't have surface charge, it's a volume distribution. So that's why electric field will be continuous. Again, so anyway, we shall discuss that one later. Okay. So now wait a second. Now what you have to do, you have to find the potential outside we already found, am I right? So that is just similar to 1 by 4 pi epsilon naught Q by R. That's it. Is that it? We already found. We shall find potential inside. How do you find potential inside? So minus infinity to capital R, isn't it? E out, am I right? Infinity to capital R means on the surface, that means outside region, isn't it? E out dot dl vector plus capital R to small r, somewhere point inside. You have to take some point inside because you need potential inside, isn't it? Origin, somewhere point here, okay? So you have to come from infinity to this point to somewhere point inside, that is at a distance r from the origin. Is that okay? Here to here. So r to small r, E in, am I right? From here to here, your electric field, you have to put E in dl vector, isn't it? Now wait a second, you have to ask question, what is the path? It's independent of the path. Okay? Only initial and final points does matter. Is that okay? Now, again, you have to ask one more question, where we have to take infinity. Whether infinity is a one point. Now that becomes too mathematical. I mean, my question is, it depends on the endpoint, am I right? Whether you are coming from that infinity or that infinity. Huh? Potential should be 0. Am I right? We have to take a point where potential is 0. That is at infinity. Or you can take infinity as one point. That's what we have done in complex analysis. Do you remember? We have taken infinity as one point. Yeah. Different concept. But anyway, yeah. Now, can you do this one quickly? I think this one I can directly write. What is dl vector? dr r cap plus r d theta, theta cap plus r sin theta d phi, phi cap. Is that okay? That's why you don't have to worry about this one. Why? Electric field is along r cap dot r cap will be non-zero, other part will not come into play. Okay? So that's why minus 1 by 4 pi epsilon naught. So q by 4 pi epsilon naught integral infinity to r 1 by r square dr, that is first part of the integral. So plus 1 by 4 pi epsilon naught q by r cube into integral r to small r dr. Check it out. I'm writing the step directly after dot product. Okay? So what is this one? Minus 1 by r. Okay, it is capital R. 1 by 4 pi epsilon naught q by capital R. Am I right? First part. So plus 1 by 4 pi epsilon naught q by r cube into r square by 2. R square minus r square whole divided by 2. Check it out. One more minus sign outside. Yeah. One more minus sign outside. Okay. So potential inside. Can you simplify? Wait a second. Somewhere I did one more mistake. Small r, not capital R cube. Somewhere you can simplify, am I right? This one, half of this one, look at here. 1 by 4 pi epsilon naught q by capital R minus of minus plus 1 by 2, 1 by 4 pi epsilon naught Q by R. Look at here, R square, R cube. Minus minus plus, isn't it? So one more part, minus 1 by 4 pi epsilon naught Q by R cube into 3 by 2. Small? By 2. One more by 2. How do you simplify? 1 by 2 are common. 1 by 4 pi epsilon naught Q by 2 are common. 3 minus R square. Yeah, that's correct. I think they will give answer in like this. Okay. Anyway, last you should be able to manipulate and you should be able to get into whatever answer they have given. Okay. That was our choice. We all should take only one choice of the reference point, isn't it? That was the argument. Or just read out somewhere. Again, I try to argue. Potential at infinity will be 0, isn't it? Usually. Infinity means you are escaping from charge distribution. You can treat potential at that point 0 because there will be no charge from your point of view at infinity. Is that okay? If you think like that, there is no potential. Potential is 0. So that's why we have chosen infinity as a reference point. Again, whenever you do integral, line integral, you have to go for that respective coordinate. Remember, don't do this one in Cartesian. Is that okay? That would be too lengthy, or may not able to integrate sometimes. Okay. So since your fields are written, look at here. Can I write ER into R cap? Vector in R cap component into R cap. So theta cap and pi cap components are 0. You have to treat like that. Once you have taken, you have to take dl vector in, again, spherical polar coordinate. Okay, infinitesimal displacement in the spherical polar coordinate. You have to take that one. Okay, yeah. So second one, again, we shall do next problem. Okay, that's the best idea because that is infinite charge distribution, and we haven't applied Gauss law for exactly this problem. So second one, 22nd problem. Find the potential at distance S from infinitely long straight wire. Here we got a problem. Why? It's not a finite charge distribution, isn't it? We can't take infinity as a reference point. But Gauss law will allow us to find electric field, isn't it? So that's why, look at here. How do I start? Find the potential at a distance S from infinitely long wire carries uniform line charge lambda. Okay, let me take it like this. Lambda, line charge lambda. So first find electric field at a distance S from the wire. Okay, axially. And let me choose this one as Z cap. Surely it is a cylindrical symmetry. Am I right? So now let me choose this is distance S from the axis of the wire. Then what I have to do? I have to run a Gaussian surface. Am I right? I have to take a Gaussian surface. Again, it's a kind of small cylinder of length L and radius R. Sorry, radius? Yes, we will not take R, radius S. And we have to apply Gauss law to that one. Am I right? So line charge density lambda, charge per unit length is lambda here. Is that okay? Yeah, speak out. Any question? Quickly. Yeah. So now look at here. We have to apply Gauss law. E bar dot dl bar is equal to Q enclosed by epsilon naught. Am I right? Again, all arguments are almost similar. So, but one more thing is electric field along S cap direction. So that's why flux through these edge surfaces are 0. Am I right? Flux through these edge surfaces are 0, isn't it? I can just write curved surface E bar dot dl bar plus edges E bar dot dl bar is equal to Q enclosed by epsilon naught. Am I right? Now, these edges will not give anything. Edges means planar surface, these two surfaces. It will not give any flux. Why? Electric field is along S cap, surface area vector will be along this cap, this direction, isn't it? So, I can get rid of this one. Now, throughout that curved surface, electric field is constant. Yeah. Why are you not speaking out? DL will never look like area vector. DL can never look like area vector. I'm not doing any strange thing, okay? Whatever you know, I'm just extending day by day, okay? Yeah. So, be confident. Be confident. Yeah, DA. Okay. Now look at here. While doing this one, again, I'm not going for coordinate geometry. Earlier, in the first class, I went for coordinate geometry. Am I right? But now I'm not interested to go for coordinate geometry. I'm going to argue electric field is constant throughout that curved surface, curved Gaussian surface. Okay. This is my Gaussian surface. Okay. And along with that one, electric field and area vectors are along the same direction. Am I right? Area vector in the curved surface is along S cap. Electric field is also along S cap. That's why I can take electric field outside. Curved area. Am I right? This is, what is this one? Curved area. That's equal to Q enclosed. How do you write Q enclosed? Integral lambda dl. Integral lambda dl. That is the enclosed charge divided by epsilon naught. Isn't it? Or you can directly write this one, because you know it is uniform charge density. What is the charge within this region enclosed by the Gaussian surface? Lambda is charge per unit length into length. Lambda into L. You can write directly lambda into L. You don't have to worry much. Okay. So now, what is this one? E. What is the surface area of this curved Gaussian surface? 2 pi S into L. Am I right? Now, this part will be same for all cylindrical symmetry problem. Lambda L by epsilon naught. It got cancelled. Now, what is this one? So, electric field is equal to 1 by 2 pi epsilon naught, or lambda by 2 pi epsilon naught, 1 by S into S cap. Check it out. 1 by S into S cap. Yeah. Now, what is the next one? We have to find the potential. Potential at a point S. Am I right? Yeah. Now, you can find potential at a point R or S, whatever. Find the potential at a distance S here. Now, how you have to do? You have to integrate from infinity to S, E bar dot dl bar. What's the problem? You can't take infinity as a reference point. If you take infinity as a reference point, look at here, when you integrate, you will get log actually. Log infinity is infinity. That's why what we shall take? We shall take some point A. No, it's not unique. So that's why if they ask any question on this one, they will ask potential difference. Okay, potential difference is independent of the choice of the reference point usually. Okay, so now, so this is our choice now. Okay, so now what is this one? Again, you are doing the integral in cylindrical coordinate. What is your dl vector? ds s cap plus s d phi cap plus dz z cap. Am I right? dz z cap. So then potential at a distance s is equal to A to S. If I have to take A, how to take? A is a distance from the axis again, okay? Are you getting my point? A is some distance from the axis. Actually, position in a space should be written in terms of position vector. Are you getting my point? Position in a space should be written in terms of position vector, okay? What I am taking distance A from the wire. Position as a distance A from the wire. Again, it doesn't matter where you are along the z axis. Why? It is infinite extent. Okay, if you are just displacing here, you will not feel any difference because it is infinity forward as well as backward. Okay, only thing that does matter for the point in space is where you are from the wire. That's it. Perpendicular distance from the wire. Is that okay? That is the symmetry actually. So now, if you take dot product S cap dot S cap, what would you get? Any idea? 1 by lambda by 2 pi epsilon naught 1 by S into ds. So minus lambda by 2 pi epsilon naught log S running from A to S. Am I right? What is this one? Ultimate answer. Potential at S lambda by 2 pi epsilon naught log A minus log S ln A by S. Negative sign taken inside. Okay, A is some point here, somewhere here. Let me choose this is a distance A. Okay, let me choose this is as my reference point. It is at a distance A from that one. Is that okay? Because I can't choose infinity as a reference point. Yeah, the question. But when he asks potential difference, you don't have to worry. Okay, it will be independent of the choice of reference point. Again, two different problems. One is finite charge distribution, other is infinite charge distribution. In both cases, we applied Gauss law to find electric field. We used the electric field to find the potential. Okay, line integration of electric field to find the potential. So next one. Problem number 2.15. What is it? Potential at the center using infinity as the reference point. Now remember, in these cases, you have finite charge distribution, but you can't apply your integration formula of potential. Okay, spherical integral would be too lengthy. Just try one example problem that he has done in the book. Wait a second. Just try example number 2.8. Okay, that is to surface integral. Again, you need to do something, and that's not that straightforward. Okay, you have to substitute. Now again, I hope you can do this one. Am I right? The only thing is you have to find electric field outside, electric field in between, electric field. Here electric field is 0. Am I right? Only thick charge distribution. Am I right? Is referring problem number 15. Okay, 2.15. So of radius A, radius B. So charge density here, that is I think K by R or R square? K by R square, isn't it? Charge density is equal to K by R square when R is between A to B. 0 otherwise. Only in that thick spherical region you have a charge. Again, the charge density varies like 1 by R square. I hope we have done how to find electric field. Am I right? Just line integrate that electric field and just do that one. Now observe one thing. Yeah, for the point outside, if you change R, your potential will change. Okay. For the point here, if you change R, your potential will change. But for the point inside, wherever you take, potential is same. Why? Inside electric field is 0. That's why whatever the point you take, it will not introduce any line integration. Are you getting my point? Suppose if you are finding, so let me take E third one, okay? E second one. E first one, that is 0, isn't it? Now you are taking R less than A inside the inner surface, okay? So then you have to integrate infinity to R, am I right? That you are going to convert infinity to B, am I right? Because infinity to B is one region, you will get one type of electric field. So from B to A, from A to R, am I right? this part is always 0. Whatever the point R you take, am I right? Because electric field is 0. So that's why only these two parts will add up. And you will get constant potential within this one. So if potential was variable, you will get non-zero electric field, isn't it? If potential is variable, you will get gradient, isn't it? You may get gradient. So that's why you will not get any potential. You will not get any variable potential. Potential should be constant here. So that gradient is 0, that means electric field is 0. Okay? Observe those facts. Again, one more question, 2.16. Yeah, I better to do that one. Sixteenth problem or 2.16. Again, long cylinders, long coaxial cable, I mean just like your TV cable, isn't it? It will contain one metal, what you call, a coating or metal, that's also wire. Have you seen that one? That's also kind of wire which is wound randomly. So inside one is thick copper wire usually. So now, coaxial cable, again he hasn't said, sorry, it's a conductor, okay? In TV cable, it's a conductor. Conductor will have different properties, okay? We shall study later. Coaxial cable carries a uniform volume charge density rho inner the cylinder. Inner cylinder contains uniform volume charge density rho. And its radius is A, okay? Its radius is A, its radius is B. And uniform surface charge density on the surface of the cylinder, and he didn't mention, yeah, let it be. But this is negative, this is positive. You should not say like that, but if you take any cross section, total amount of surface charge is equal to total amount of volume charge within that one, so that it is electrically neutral. He's saying like that. Is that okay? Total amount of surface charge, negative surface charge. Surface charge is negative. Is that okay? You got to write minus sigma. So total amount of surface charge, that is equivalent to, if you take any cross section, suppose I have taken length L, just take it like that, okay? Length L. Is that okay? Now total surface charge outside, negative surface charge outside is equal to total volume charge inside, positive. Okay, they will cancel out each other, so that we can say it is electrically neutral. Okay, we can say it is electrically neutral. Let me read out the sentence. Wait a second. The surface charge is negative and is of just the right magnitude that the cable as a whole is electrically neutral. Okay, whole is electrically neutral. Are you getting the idea? Now, next one is find the electric field in all three regions. First we shall find electric field, then we shall go for potential. Okay. How do you take electric field outside? Region 1. This is my Z cap. Is that okay? Z cap of my cylindrical coordinate. Now when S is greater than B, isn't it? When S is greater than B means outside the outer coating. Am I right? So that's my first region. Okay. So now if you apply your Gauss law, E bar dot dA bar, E bar dot dA bar. Now we have to ask some question. I have to take one Gaussian surface like that. Am I right? Why? Charge enclosed is 0. That's why electric field is 0. But what about flux of electric field in this part of the region? Because inside electric field may be non-zero. Am I right? Gaussian surface is a closed surface. Part of the surface pierces into this region. Am I right? Are you getting my point? You should have a complete argument. Are you getting my idea? Don't think only about curved surface which runs outside, isn't it? Gaussian surface is a closed surface, isn't it? But this planar surface will not contribute again. Inside, if field exists, it should be along S-cap only. It should be actually outward only. Are you getting my point? So because of that fact, again, this planar surface of my Gaussian surface will not contribute anything. Again, what would happen? So only you have to do curved surface integral. So that is electric field dot dA vector curved surface integral is equal to Q enclosed, that is 0, and it will come out, isn't it? Electric field will be along dA vector, and electric field depends only on axial distance. Yes, that's why it will come out. Are you getting my point? Planar surface integral. So if it, even though electric field, are you getting my idea? This is what I am talking about, isn't it? It will pierce, Gaussian surface will pierce this region. Is that okay? So that's why you have to take care of that one, but argue that corresponding flux equal to 0, corresponding surface integral is 0. Why? Even though there exists electric field inside, it will be like this. Your area vector will be like this. That's it. Is that okay? Don't only think about outside. Okay? Yeah, these imaginations are needed because later when we get into dynamics, you should know how your surface integral runs. Where are the surface? Okay? That's imaginary surface. It can pierce into the wire. Don't hesitate to do that. Are you getting my point? Gaussian surface is an imaginary surface. Yeah. Question. No. He designed the question like that. Okay, he designed the question. Suppose if you take one fraction of that wire, one length of that wire. So net negative charge outside coating is equal to net positive charge in the inside core. That's how he designed question. Okay, not any practical question. Not even conductors. Okay, he hasn't mentioned conductor. He will discuss later. Okay, he will not mention. Obviously, conductor. If you charge that one, it will not be volume charge. Am I right? It will go to surfaces. We shall discuss that one. Okay. So property of conductor is different. But are you getting my point? You should have complete imagination of the surface where it is running. Okay. So that's why this electric field will come out. What is this electric field? Electric field on the surface, and that's why it is 0. First region, electric field equal to 0 or null vector. So second region, isn't it? If I take Gaussian surface in the second region, am I right? At a distance S. Now my S is between A to B. Second region. So in between those, then obviously this part will be mod of E into 2 pi S into L. Let me write directly now. Cylindrical symmetry. Am I right? What is Q enclosed? What is Q enclosed? Now you have to do that integral. Am I right? Integral rho d2 whole divided by epsilon naught. Now there are no charges in the space. Only charges enclosed in this region, isn't it? Now you have to do that volume integral. Rho will come out. Integral of d2. Am I right? Because rho is constant. He said uniform positive charge density. So what is integral of d2? What is the volume of this region? Radius a. Length L. And don't go for again coordinate geometry. Even if you go for coordinate geometry, you will get the same answer. Okay, write it directly. Only if this is a function, you have no choice. It will come out now. Look at here. That's why a rho into what is the volume of this region? Pi a square into L by epsilon naught mod of E into 2 pi S L. Okay. So pi also got cancelled. Pi also got cancelled. What is this one? Electric field in the second region, that will be equal to rho by 2 epsilon naught. Am I right? Rho a square by 2 epsilon naught 1 by S into S cap. Yeah. Question. So what is third region? Third region means when S is less than A. S is less than A. Inside the inner one. Now again, if you apply Gauss law, E bar 2 pi S into L, this part will be same. Now you have to take a Gaussian surface inside the inner one of length L. Don't ask question. This is L, this is also L. Okay, that's your convenience. Okay, and again, axial distance S. Okay, now look at here. While finding this one, you have to take care rho d2 by epsilon naught. Obviously, rho is outside. Now, what is the volume? Pi S square into L. Why? You have to take volume within that region, isn't it? Pi S square into L. Pi S square into L. That is the difference. Look at here. Obviously, you will get different functionality. 2 pi S L. L got cancelled. So, pi got cancelled. So, S will come to the numerator. Am I right? S will come to the numerator. So, can I write in all three regions? If you got any confusion, write it down and so ask me, okay? So try that one. First region, outside 0 when S is greater than. Second region, when S is between A to B. What is this one? Rho A square by 2 epsilon naught 1 by S, S cap. Electric field in the third region. Rho by 2 epsilon naught S cap. Yeah, it's not over. Our aim was to find the potential difference. What he asked? No, find the potential at the center by choosing infinity as a reference point. Isn't it? If you choose infinity as a reference point, potential at 0, can I write like that? Find the potential at the center using infinity as your reference point. Which addition you are looking? Different? Different. Okay. No, problem number 23, that's what I am talking. Okay. 24th problem, isn't it? For you, I think you asked, he asked potential difference, isn't it? Yeah, sorry. I jumped off one problem, all right? Find the potential difference between a point on the axis and a point on outer cylinder. I mean, potential difference. How did you return? Any idea? VB minus VA minus integral of A to B. Don't forget, okay? You have to remember. If you got reverse, that option will be there. Okay, be careful. E bar dot dl bar. Wait a second. This is one point, this is another point. It's a potential difference between B and A. Am I right? Point B and point A. Generally, B is some point in space, A is some point in space. Am I right? We have written position vector. Now, what he is asking? Potential difference between, speak out, a point on the axis, point on the, so what we have to take? VB minus VA? Okay. I mean, now I have to take A as 0, okay, A as some point on the axis, B as point on the outer cylinder. Is that okay? That's better, isn't it? Now again, V of B minus V of 0, that's equal to minus 0 to B E bar dot dl bar. What is this 0 to B integral? That is your axial distance, okay? Axial distance. You can take any 2 points, isn't it? You can take any 2 points. I mean, your potential again, so because of symmetry, whatever the point you take, these are equipotential surfaces actually. Okay, whatever the point you take, you will get the same potential. Are you getting my point? These cylindrical surfaces, they are equipotential surfaces, isn't it? That's why you can take any point on the axis, any point on it. He didn't specify it, am I right? These two should be actually outward, isn't it? It doesn't matter. All of these points are at the same potential. All of these surface points are at the same potential because of symmetry. Is that okay? Just 0 to b, just integrate from 0 to b. What would you get? Now you need to take two parts, this one to this one and this one to this one. Am I right? So that's why. So 0 to a, so that is your third region. Am I right? Dot dl bar. So plus a to b, second region. Am I right? Do that one quickly. Again, how do you write dl vector in cylindrical coordinate? Dl vector is equal to ds into s cap plus s d phi cap plus dz. No problem. Wait a second, yeah, he's talking about continuity of the electric field. We better talk about that one later after discussing boundary conditions. Okay, wait a second. Then, so VB minus V0, that's equal to minus integral 0 to a, what is E third? Rho by 2 epsilon naught. Rho by 2 epsilon naught. S ds. 0 to a s ds, check it out, plus rho by 2 epsilon naught a square, second region, 1 by s, a to b, 1 by s ds, check it out, minus rho by 2 epsilon naught, let me take out, okay, a square by 2, plus a square into log of log b minus log a, here in this formula. Wait. What happened? Yeah. Vb minus Vi is equal to integral a to b. Is this? Yeah, definitely. I have taken like that while doing the integral. Okay, I mean these are actually point in space. I mentioned that one. These are point in space. Now one of the point is your any point on the axis. Other point is any point on the outer of the what you call coating or what you call. That's why I mean I haven't put vector. Why? You have to ask question. I don't need vector because I can take any point on the outer surface. I can take any point on the axis. So I don't have to write that one as a vector. So I just have written that one like this, but we should know that one. One is point on any point on the axis, other is point any point on the outer surface, because those surfaces are equipotential. Okay? Yeah. Log of b by a. Am I right? Check it out and compare your answer from the solution. Now, observe one fact here. Electric field is continuous here and here. Look at here. If you put S equal to A, you'll get this is equal to this one. Isn't it? But if you put S equal to B, you will not get this one. Discontinuity. Whenever there is a surface charge, he said this, there is a surface charge in the outer surface. Am I right? You will get electric field discontinuity. We shall derive it. Okay, boundary conditions. Whenever there is volume charge, there will be no discontinuity, because here this is a volume charge and it is empty space here. From here to here, electric field will not suffer any discontinuity. But here to here, you got a surface charge. Whenever there is a surface charge, electric field will suffer discontinuity, definitely. Okay? Yeah. Think over it, okay? Each and every step. Okay, I think you can do the rest of the problems, okay? So tomorrow let me start with boundary condition. I think one or 2 days we can finish it up, okay? Have you tried one outside problem that I told that appeared in old question paper? And many problems appeared in old question paper. 50th problem, 2.50. And it needs your Dirac delta formulas. Okay? Try that one, 2.50. And that 2.52, we shall do that one. That was also old question actually. Little lengthy. Have you tried these two problems? Last two problems from Gauss law? One is thick slab, other one is two sphere merged. Last two problems. Try them. Let me solve tomorrow evening. Okay.